In this video, we're going to take a look at the strengths of acids and bases using Ka and Kb, the dissociation constants. An acid is defined as strong or weak based upon how well it ionizes. Things that ionize completely, like hydrochloric acid, sulfuric acid, and nitric acid, are all classified as strong acids. Every other acid from there is a weak acid because it only slightly ionizes. And there's a whole different range of how well or not well it ionizes in terms of weak acids. So looking at acetic acid like vinegar or carbonic acid, we can use that Ka to determine just how strong or weak it is. So looking at acetic acid, we see less than 1% of the acetic acid that is dissolved in actually ionizes, resulting in H plus or H3O plus ions, as opposed to hydrochloric acid where you have 100% ionization. Every molecule that dissolves in will dissociate and give these H plus or again H3O plus ions. So looking at the equilibrium constant, we would see that the amount of H plus or H3O plus ions and the conjugate base related to the amount of water and acid when it gets to its equilibrium would give you an idea of what that ratio is. And again, the amount of water is constant and it's a much larger value than the overall amount of ions that actually are there being dissociated into water. So we can kind of ignore the water, move the water out of there. And again, it gives us our Ka, which is the amount of ions, our H plus or H3O plus ions, and our conjugate base versus the amount of acid that didn't dissociate. So ones that have a very small Ka are weak acids, and ones that have large Ka are stronger, and you can compare one acid to another based upon how well it dissociates, how many ions you're getting, again, relative to the amount of acid that you put in. For polyprotic acids, so when you have a second and a third hydrogen ion that's going to dissociate and give ions, we can pretty much ignore those other ions. They're not going to have much effect on the overall amount of ions that are in there because you're taking a fraction of the hydrogen ions that are being dissociated in. So you're talking 10 to the negative fourth and fifth and sixth powers of dissociation for the first H, and then doing that again for the second H. That's such a small amount relative to the overall hydrogen coming from that first H that goes in, we can pretty much ignore it. So let's take a look at how we'd solve for a Ka for a given problem. So if we have 0.1 molar solution of some monoprotic, so just one hydrogen acid, that is going to result in an H plus ion concentration of 1.34 times 10 to the negative third molar. What is the Ka going to be? Well, I know Ka is the H plus concentration times the conjugate base over the amount of acid that didn't dissociate. So we know how much of our acid we put in to get our molarity of 0.1, and we know how much H plus there is when we are all said and done, so now we can kind of figure out the other pieces of this puzzle. So here's our equation when it gets to equilibrium, again with our acid, Ha, going to water to dissolve in to give our H plus ions or H3O plus when it gets together with the water, and our conjugate base A minus when it's lost the H plus. So we're going to set up our table here, ICE, initial change equilibrium, and taking the information we have and kind of filling in the puzzle pieces, looking at the balanced chemical equation, we can come up with our values at equilibrium for our H plus, our conjugate base, and our acid. So we know that we started again with a 0.1 molar solution of our acid. The amount of water, again, we don't really care for, so we'll just put an X there. And then there was no H plus ions or no conjugate base ions when we originally put this in to begin. So the next piece of information we can fill in is the fact that at equilibrium, we know the H plus concentration is 1.34 times 10 to the negative third. So if there was none to start, and that's where we finish, we know the change is 1.34 times 10 to the negative third. Then from there, I can say, well, if there's a 1-to-1 ratio of my H3O plus to my conjugate base, again, because it's monoprotic, then I know the change for my conjugate base is also 1.34 times 10 to the negative third. And then lastly, for my acid, I know, well, if they're a 1-to-1 ratio, then I used up that 1.34 times 10 to the negative third for the amount of acid that I began with. So then, again, we don't really care about the water, and we can fill in the rest for at equilibrium for our acid and our conjugate base. So we know that of the acid, we have 0.009866 molar left. And then for our conjugate base, again, if it's a 1-to-1 ratio, we made 1.34 times 10 to the negative third concentration of our conjugate base. So lastly, now we can just fill into our equation that we have each of these concentrations, and we find that, again, our H plus is 1.34 times 10 to the negative third, our conjugate base is also 1.34 times 10 to the negative third, and our acid that didn't dissociate is that 0.009886 molar, and then we find our Ka to be 1.82 times 10 to the negative fifth. So again, a pretty weak acid, very small number. I also can use this to relate Ka with pH. So I know that the initial concentration of the weak acid along with the pH, I can solve for an H plus concentration, or conversely, I can use the concentration with the Ka and determine a pH and the amount of looking at the percent of ionization of that particular weak acid. So let's take a look at how we can solve for a pH when given a Ka. So we know we have hypochlorous acid, so we're looking for hypochlorite, which is ClO, 1H to balance out the minus 1 of the ClO, and we know that the Ka is 3 times 10 to the negative eighth. If I have a 0.5 molar solution, what is the resulting pH of that solution, and then also what is the percent ionization? That'll be important in a second when we get to the end. So here's my chemical reaction. You have our hypochlorous acid being put into water, and then it gets to equilibrium with our H plus ions and our hypochlorite ion, our conjugate base. So we set up our table, again trying to figure out what is the amount of H plus and ClO minus relative to the amount of HClO that did not dissociate and dissolve into solution. So I need to figure out how much there is of each, knowing that my Ka is 3.0 times 10 to the negative eighth when it gets to that equilibrium point. So we got to do some filling in backwards here. Again, we know how much of the HClO we put in originally, are 0.5 molar. And again, we don't care about the water, and that there was no H plus ions or ClO minus ions to begin. However, that X is going to get a little bit tricky here, so we're going to ignore that X. We're going to X out the entire column for water because we're going to have to use X as a variable in this particular case. So we don't know how much was used and how much we have at equilibrium. We're going to have to, again, use a little bit of algebra here. So we know that for every one HClO that dissolved in, that we got one H3O plus and one ClO minus. So we're going to use X. So we can use minus X and plus X for the ones that were used versus what is made. So then we know that at equilibrium, we have for our HClO that 0.5 minus how much got used up. And then for our H3O plus and our ClO minus, well, there was none to begin, and we made X, so at equilibrium we have X for both. So plugging these values into our Ka equation, again, if H plus is X and ClO minus is also X, we have X squared over our HClO, which is the 0.5 minus X. And that all equals 3 times 10 to the negative 8. Now, again, being a weak acid, we know there isn't a whole lot of ionization that happens, so the amount of HClO that is actually going to dissociate is very little relative to the amount that we started with. So we can go ahead and assume that we can ignore that X on the bottom. So we're going to call it just 0.5, because again, there's so little relative to, it's such a small percentage, which is where we're going to get to in the end. We look at the percent ionization to make sure our assumption is good, that we can just ignore how much was actually used up. It's pretty much the same as 0.5. It's going to be very little different from it. So now we can algebraically solve for the X that is going to be our H plus concentration and our ClO minus concentration. So if we multiply both sides by 0.5, we end up with 1.5 times 10 to the negative 8. And then take the square root of both, and we find that our X is 0.0001225 molar for our H plus and our ClO minus. So now we very easily can go ahead and solve for our pH, because we know our H plus concentration is this 0.0001225. So plugging into our pH equation, where pH is the minus log of our H plus concentration, substituting that on in, we find that our pH is 3.91. And again, that's below 7, so it is acidic, so that makes sense based upon the amount of H plus that is here. Certainly that's H plus, not OH minus going in, that we would be acidic. And it is a weak acid, so 3.91 is down into the acid side of the pH scale, but not anything close to what we'd see with a strong acid like hydrochloric acid or sulfuric acid. So then lastly, that percent ionization, again, that's going to let us know that our assumption is okay. If it's too large of a percent that actually dissociates, and it would throw off our assumption as far as how well our calculation would be, assuming that the amount of change for our actual acid is very little. So let's go ahead and take a look at the amount of ions that dissociated versus the overall amount of acid, and again make a percentage of it. And again, if it's 0.0001225 H plus ions versus that 0.5 HClO acid that went in, we see that it is, again, is a very low percentage, 0.0245%. So since that is such a small percentage, we can go ahead and say our assumption is okay, that we can assume that the amount of acid that was actually dissociated relative to how much there was, again, was so little that 0.0245% isn't going to really change our resulting answer that much. And for bases, we can do the same exact thing. Again, bases dissociate into water, giving hydroxide ions, not H3O plus or H plus ions. However, we do have strong bases and weak bases, ones that will completely dissociate and ones that won't. So for the ones that are only partially dissociate, we can get our Kb. And again, our Kb is very much the same as our Ka, but instead of our conjugate base, we have a conjugate acid. Instead of H plus ions, we have our OH. And again, instead of amount of acid that didn't dissociate, we have the amount of base that didn't dissociate. And again, just like that of acids, a large Kb means a stronger base, and a smaller Kb means a weaker base. But not to be confused with concentration. So concentration versus strength. Concentration has to do with how many particles are you dissolving in per volume, the molarity. If it is concentrated, you have a lot of moles in per volume, and if it's dilute, you have very few. Strength has to do with what percent actually ionizes. Of the molecules you're dissolving in, what percentage of them are actually breaking apart and giving H plus or OH minus ions. So you can have a very concentrated strong acid, like if you had 12 molar hydrochloric acid, that is as strong a concentration as you can have with hydrochloric acid, and again, all of the hydrochloric acid molecules are going to dissociate. But you also could have a dilute strong acid. Again, hydrochloric acid, you could put very little into a whole lot of volume, and you would still have 100% dissociation, but very little H plus ions because you put very little in. You can have a concentrated weak acid. You could have as much acetic acid or vinegar dissolved in it as possible, but again, only partially is it going to dissociate, so you're still not going to get a whole lot of H plus ions. Or then lastly, you could have a very dilute and weak acid again, so put very little acetic acid in, and then from there even have a smaller percentage of that dissociating, so you get very few H plus ions. And the same thing happens with bases, for strong bases and weak bases in concentrated and dilute.